Problem 17. Problem 17. The three-dimensional figure above has two parallel bases and 18 edges. I could try to draw it, but, well, hell, let me draw that. Let me draw that. So the base, their bases are both hexagons, essentially. So I have one base that looks like this. Maybe I should draw it with, well, let me draw it. I have time, so let me draw it properly. So the base in front looks like something like this, like this, like this, like this, like that, and then the top base is just a small version, or a smaller version that looks like that. Whoops. And then they draw, these are the front edges, look something like this. I'll do the rear edges in a darker color just so you know that they're in the back. It's there. This is the rear edge. Well, I should have drawn them later because they're. So let me switch back to this and just paint over this just so you know that these are in front. Those are in front. Okay, good enough. And they tell us that this point up here is V. I don't know if that even fit on the video, but hopefully you can see that point up there. The three-dimensional figure above has two parallel bases, right? This is one base, that's the other base. Two parallel bases and 18 edges. Line segments are to be drawn connecting vertex V with each of the other 11 vertices. Each of the 11 vertices in the figure. How many of these segments will not lie on an edge of the figure? So an edge of the figure is essentially, well, let's see what they're saying. They're saying, okay, 17, line segments will be drawn connecting vertex V with each of the other 11 vertices. So what are the other 11 vertices? Let me draw them. This is 1. Let me do it in a brighter color. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And they want to know how many of these segments will not lie on an edge of the figure. And I actually think this is a little ambiguous because if something is on the face of the figure, on a base, okay, well they're saying the edges. They're defining the edges as the line. So, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 edges. So it can lie on a face and still count. So how many of these line segments can I draw? Well, if I want to draw a line segment with every point on this base that is not on an edge, so this one won't count, right? Because that is on an edge right there. But I could draw 1. Oh, I should do a different color because this is going to get messy. I could draw 1, 2, 3, right? Because I'm connected to the other two with an edge. So I have 3 there. And then how many can I draw a line segment to on the other that I'm not connected already with an edge? Well, the way to think about it is this point is connected to this only here, right? So we can't use this as one of the line segments. But then there's 5 other points that it can connect to where you're not going through an edge. So you're going 1, 2, 3, 4, 5. So there's 5 more. 3 plus 5 is equal to 8. And if you wanted to do that even without drawing it, you could have said, well, okay, there's 2 types of vertices. There's the ones that are on the top base and the ones that are on the bottom base. On the top base, which was a hexagon, right? And this was our point right here. On the top base with the hexagon, there are 5 other vertices, right? 1, 2, 3, 4, 5. But you're connected directly to 2 of them. So there's only going to be 3 that you can go where you're not already connected to them. And likewise on the bottom base, if this was the bottom base, vertex V was only directly connected to this one, right? It had an edge directly to that one. But the other 5, it didn't have a direct edge to. So all of those would have been fair game for the problem. So 5 on the bottom it can connect to, and 3 on the top. And that's where we got our 8 from. Next problem. This looks like something that I need to draw. That's my x axis. That's my y axis. Let me label them x, y, and then they drew a rectangle. I'll do it in a different color. It looked something like this. Looks like that. And then how did they label it? They said that this point C is the point 1/2, comma C. This point B is the point -1/2, comma B. -1/2, comma B. My microphone's hitting my sweatshirt. And then, let's see, this point here, A, is -1/2 A. And then finally, this point here, D, is 1/2, comma D. And then they drew a graph in between this whole thing that intersects. It goes from here. It starts to flatten out. It's already looking kind of like an x-cubed graph, if you're familiar with what an x-cubed graph looks like, and it goes through that point. Of course, there's a point here. Okay. Note figure not drawn to scale. In the figure above, A, B, C, D is a rectangle. Points A and C lie on the graph of y equals px cubed. Right. This is y. It looked like y equals px cubed. Fair enough. Where p is a constant, if the area of ABCD is 4, what is the value of p? So, area is base times height, right? Can we figure out what the base is? Well, sure. We know that this is 1/2, right? Because the coordinates of these two, the x-coordinate is 1/2. We know that this is -1/2, because the coordinates of these two are, the x-coordinate is -1/2. So, if this is 1/2, this length is 1/2, this length is 1/2, we know this entire base is 1, right? So if we know the area is 4 of this entire rectangle, what is this height? This height, this distance, is going to have to equal 4, because 4 times 1 is the area, and 4 times 1 equals 4. So this has to have height 4. And this is symmetric, right? Because, well, do we know that it's symmetric? Well, we do. Actually, do we know that it's a symmetric? It's a rectangle, points lie on the graph. Do you know how we know it's symmetric? Because this is y equals px cubed, and anything that is px cubed would be symmetric like this. That as far at 1/2, whatever point it is at C, it would be at a similar point down here, right? But it would just be on the other side and in the third quadrant. So it's kind of like you're flipping it over the origin. But anyway, so if we assume that that's symmetric, then we know that this distance is 2. This distance is -2, right? If this distance is 2, then now we know a point on this graph. We know that C must be equal to 2, right? Because that's the y-coordinate. Now we have a point on the graph, and we can substitute it back in. Y equals px cubed. So let's put 2 for our y, because we know that that's a point on the graph, right? We know the point 1/2, 2 is on the graph. So if we put 2 for y, we get 2 is equal to p times the x value. P times 1/2 cubed. 1/2 cubed. So 2 is equal to p over 8, right? 1/3 cubed. Oh, sorry, sorry, I can't do math. I did 1/2 over cubed. 1/3 cubed is 27. No, it's, yeah, right, 27. 3 squared, 9, 27. So p, multiply both sides by 27, is equal to 54. And all we did here is we just said, well, let's figure out what this side is. We know that this side is 1 because we can look at the -1/2 and the 1/2. So this side has to be 4. If this side is 4 and it's symmetric, it goes just as much as above the x-axis as below, and we know that because this is an x cubed function. We know that this side must be 2, or that the y-coordinate is 2. And then we just substitute into y is equal to px cubed to solve for p. I'll see you soon.